Hello, today I'll be presenting our work on HyperSPNs, compact and expressive probabilistic circuits. One key task in machine learning is density estimation. Given a bunch of data, we would like to learn the underlying distribution so that even without the data, we can sample from our distribution, or we can ask about the density of different points on our distribution. For example, here one point is more likely than the other. Finally, we might be interested in probabilistic inference queries. For example, we might ask, what's the probability of a point being in this highlighted region? Probabilistic inference queries such as these, or marginals and conditionals, can be useful for various applications. For example, consider that we've learned a distribution over roads on a map, as shown here, where we have roads 1 to 100. We might be interested in the query, what's the probability that road 1 is under construction? This simple query actually requires us to marginalize out over all the auxiliary variables. In this case, this is roads 2 to 100, and doing this can be intractable. We might also be interested in the question, what's the probability that road 7 is busy given road 9 is under construction? And this conditional probability might be expressed as two marginals. So for both the numerator and the denominator, we need to integrate out over a whole bunch of variables, and this is also intractable. So in general, if we only have access to the density of our distribution, computing marginals and conditionals can be difficult. This leads us to the choice of the modeling family that we use. On one hand, we can use simple mixture models that are tractable and allows us to answer different types of probabilistic inference queries. And on the other hand, we can use more expressive neural network-based models. There's one caveat here, which is that even with simple mixture models, if you take an infinite number of mixtures, your model can be as expressive as you want. So instead of writing expressive here, we should be talking about expressive efficiency. And more expressive efficient models, such as the neural network-based models, include GANs, flows, VAEs, and score-based models. And somewhere in between, we have models that are more tractable than neural network-based models, and also more expressive than simple mixture models. For example, determinantal point processes, sum product networks, or arithmetic circuits. And these models allow us to compute marginals and conditionals tractably and is more expressive than mixture models. In this work, we'll be focusing on sum product networks, and in particular, we'll be looking at how to train large sum product networks with good regularization. So what are sum product networks? At its core, it's made up of a bunch of base distributions, and these can be simple, such as univariate Gaussians. And we can add sum nodes, which takes mixtures of distributions. And we can also add product nodes, which we can think of as factorizing distributions. These sums and product nodes can be stacked together to form a feed-forward network that defines a computation graph, which we can evaluate bottom-up to get the density of a point in our distribution. We can also train this via gradient descent through backpropagation. So this can be used in a very similar way to neural networks. Another way of viewing sum product networks is that since we're only taking sums and products, the computation graph defines a multilinear polynomial over the base distributions. And this property allows us to write down many tractable algorithms for computing probabilistic inference queries, such as marginals and conditionals. In particular, we can compute marginals in just one forward pass. So recall earlier, we were looking at the toy example over roads, and we were asking the question, what's the probability that road 1 is under construction? To answer this question on a sum product network, we simply set the variable x1, representing road 1, to the value that we want, which is under construction. And to marginalize out all the other variables, we set all of them to the constant 1. and evaluating this network in one forward pass gives us the answer to our marginal query. So now that we know how sum product networks work, the question is, how do we actually learn the structure, the architecture of a sum product network? And by this, we're referring to the edges and the nodes, how they stack together in our network. One approach is to do structure learning, where we have an outer loop that decides where to add and remove edges, but this can be expensive. Another approach is to look at prescribed structures, where we simply define a bunch of sum and product layers, and we stack the layers one after another, very similar to how people train neural networks as well. So two particular prescribed structures that have been proposed are RAT-SPNs and EiNETs. And EiNETs report training up sum product networks of up to 9.4 million parameters. So if you'll recall before, we said that sum product networks might not be as expressive efficient as neural network-based models on the right. But still, the bigger the network, the more expressive the model. So if we can train larger sum product networks, we can get a more expressive model while still supporting tractable queries for marginals and conditionals. This raises the question, how large of SPNs can we train? One issue with training large SPNs is that of overfitting, and a couple of regularization choices people have looked into include dropout, but this only works for discriminative settings. There's also weight decay, which is a reasonable choice, but this still gives the SPN many parameters and many degrees of freedom. In our work, we propose HyperSPNs, which give the SPN few parameters while being memory efficient and giving better generalization, all while still training the same large underlying sum product network structure. Here's how HyperSPNs work. Since we're using a prescribed structure, we can abstract away the edges in our network and just think in terms of sectors of weights. For each set of parameters between two layers of nodes, we can treat them as one sector of weights. Then our entire HyperSPN can be boiled down to a set of these sectors of weights. So if we can materialize these sector of weights, then we have our SPN. Unfortunately, these sector of weights are high dimensional and can be prone to overfitting. So to regularize them, we introduce low dimensional embeddings, using one embedding per sector of weights. Then we train a deterministic mapping using a neural network that maps the low dimensional embeddings to its corresponding sector of weights. This entire architecture can be trained end to end, where we start off with our low dimensional embeddings that we pipe through a neural network to materialize our SPN. Then given our SPN, we can evaluate it on the data as in standard density estimation. Then we can back propagate through the SPN through our neural network and back to the embeddings. Here the SPN is denoted in gray because it actually has no trainable parameters. Its parameters are a deterministic mapping of the embeddings and the neural network, which is what we're actually training. To see why HyperSPNs might help with overfitting, here's a toy example where from some underlying distribution we sample a bunch of data with the training data in blue and the testing data in orange. Then we can fit a large SPN on this data, where in red we show the areas where the large SPN assigns high probability. Since the large SPN can represent many clusters that are not constrained, it is prone to overfitting on the training data. On the other hand, if we use a small SPN, it underfits on the data since it cannot represent that many clusters. Finally, using HyperSPNs, since the underlying sum product network is still large, we have access to many clusters, and we're constraining them by using a shared neural network and low dimensional embeddings, and this allows us to not overfit on the data. We can see this in action by looking at training curves as well, where these dashed lines show the performance on the training data. We see that the large SPN is able to fit the training data the best. But when we consider the validation data, we see that the large SPN has shown some signs of overfitting, and instead the HyperSPN shows the best generalization performance. And here are results on benchmarks with binary variables ranging from 16 variables to 1500 variables. On the left, we see the performance when using weight decay, and on the right, we see the performance when using HyperSPNs for regularization. We see that we give better log likelihoods while using fewer number of trainable parameters when using HyperSPNs. In summary, HyperSPNs regularize by encoding parameters with a small neural network and using low-dimensional embeddings. This gives us better generalization while being more memory efficient and keeps all the tractability of some product networks, such as computing marginals and conditionals in linear time. And here you can find our paper and code in this QR code link.